For number 5, in order to use this equation, you have to convert to radians per second. One rotation is equal to 2 pi radians, which is the same thing as 360 degrees. So to convert that, rotations per minute. So one rotation is 2 pi radians. So that would give us radians per minute. We want radians per second, so we're converting from minutes to seconds. The other thing, this is a ridiculous speed for like that would kill anybody. So that it should be like 20 rotations per minute. So, all right. Lesson 3 on gravitation. So, Isaac Newton not only gave us 3 laws of motion that are foundational to introductory physics classes, he also came up with a law of gravitation that can be applied anywhere in the universe. Kind of like the Einstein of his day. And that equation is this. Gravitational force is equal to G m1 m2 over r squared. And here's what each of those variables are. This is gravitational force, which is measured in newtons, so force. G is a gravitational constant. This is 6.67 times 10 to the negative 11th. That is always that number. You will not have to memorize that. I will give that to you. M1 and M2 are masses of 2 objects. M1 and M2 are masses of 2 objects. R is the distance of separation between the center of masses of 2 objects. So M1 and M2, these are subscripts. It's masses of 2 objects. R, this is squared. This is not a subscript. That's squared. It's the distance of separation between the center of masses of those 2 objects. Okay. So, tell your neighbor what would cause the gravitational force to increase, assuming that you can't change this constant. Okay, what would cause this to get bigger? Okay. Hopefully you said increase the mass, decrease the distance between the two objects. Okay. What'd you say? Ooh. We want to make this bigger. This is directly related. So as these get bigger, this gets bigger. As this gets smaller, this gets bigger. What's the biggest number there? 1/2. So as x gets bigger, what happens to a? That makes sense. It gets smaller. Inversely related. Okay. All right. Just talked about that. All right. So what this law says is this. Any two objects that have mass, there is a gravitational force of attraction between them. Do you have mass? Do I have mass? So according to this, there's a gravitational force of attraction between us, pulling us together. So why isn't it like when you walk in this room, we're all not like dog pile? Sorry, gravity. Oh, this is awkward. I'm sorry. Like why doesn't that happen? Is this a big number or a small number? Super crazy small. Okay. I have some amount of mass, as you know, so do you. We're not that far away from each other. But when you multiply it by this, it makes it so insignificant that you wouldn't ever feel it. So in order to have something that has appreciable gravitational force, you need the mass to be at least times 10 to the positive 11th to counteract this guy. That's like 11 zeros. So we're talking like planets, moons, stars. Get with that? Okay. So, oh, this is another thing. I'm just checking a box on state standards on this one. So, inverse square law. inverse square law, like it's a mathematical, has this format to it. We find that because it's 1 over r squared, the gravitational force. The reason why we're highlighting this is because this pops up in other places in nature. Like there's other equations that are inverse square law. If you were to graph this, like this math class straight up, it's going to look like that. Where it's going to get weak really fast. Right with that. Inverse square law. There it is. All right. Make it a little more relevant. Pull out your calculators. Okay. Take your weight in pounds. I want to convert that to newtons. How much do you weigh in newtons? To do that, take your pounds and multiply that by 4.45. Take your weight in pounds and multiply by 4.45. That could be encouraging or discouraging depending on which way you want to go with that. But put an N by that. That's newtons. Okay. I also want to find your mass in kilograms. So take your pounds and divide it by 2.2. Take your pounds and divide it by 2.2. If you were in Europe, this is what you would write. How many kilograms you are. Okay? That could be encouraging or discouraging depending on which way you want to go on that one. Okay? Good with that. Have those jotted down, put a kg by that one. That's your kilograms. All right. What we're going to do is we're going to calculate the gravitational force between you and the Earth. So you're going to stand on Alaska. And I want you to calculate the gravitational force between you and the Earth. So what do you think the two objects are that we're going to find the mass? The Earth and you. Okay? The Earth's mass is 5.97 times 10 to the 24th kilograms. Folks, that is 24 zeros. Significantly bigger than 11 zeros. Okay? And you have your mass in kilograms. Okay? What is, so the distance of, so R is the distance of separation between the centers of mass of the Earth and you. How would you go about finding that one? Center of mass of the Earth is, well, at the center, at the core, center of the core. Center of mass of you is about your belly button. Okay, so that distance there. Now, if we were measuring the distance from here to the Pacific Ocean, would it really matter if it was high tide or low tide? Not really. I mean, we'd measure it in miles, and like high tide, low tide is going to add a foot or two. Okay. Adding the radius of the adding half of your height to the radius of the Earth is even more ridiculous than trying to account for high tide, low tide, measuring the distance from here to California. Okay, so it doesn't matter. So we just find the radius of the Earth. Okay, so 6.38 times 10 to the sixth is the radius of the Earth. Here's a quick calculator lesson. You need to know how to do scientific notation. Typing out times 10 to the caret power. Folks, that's old school. You got a calculator that can handle that. Okay? I'll give you a quick tour of popular calculator versions. TI, Texas Instrument. Okay? The scientific notation button times 10 to the is the EE button, which is above 7, and it's like in the second function, times 10 to the, that takes care of times 10 to the. So you're going to type in 6.67, second EE button, negative, not subtract, but negative 11. Okay? If you have a Casio, okay, they have an EXP button or a times 10 to the N button or times 10 to the X button. Okay? So hit that for times 10 to the. If you have this kind of calculator, one that doesn't have a backspace, life is going to be a little more challenging for you. Okay? Parentheses are going to be your friend. Parentheses are going to be your friend with any calculator, but especially this one. My recommendation, so here they have an EE button above the 7. For these type of calculators, I would highly recommend hitting equals often and writing down what it is equal to, because if you mess up, you don't have a chance other than to like clear everything and start again. Not that advantageous, but it's better than doing it by hand. Okay. Cell phone apps, well, it totally depends on your app. You're on your own to figure that out. But in general, here are the two popular errors. Number one, you screw up on your scientific notation. The second thing is you forget to square the radius. Parentheses are very popular, helpful for this expression. Okay. So what I want you to do is calculate your gravitational force between you and the Earth. Go. To check to see if you got it right, take that number and divide it by your mass in kilograms, and you should see a number that you recognize. Which is really close to. There it is.
Get me in 8th grade.
Is that, you recognize that? Wow, dude.
Oh, he's pretty handsome.
Yeah.
So he looks like Goldenberg.
It's a solid entry, man.
That's right.
I don't know. I'm asking. Nope.
That's awkward.
Very good. Do parentheses here.
I did. Why?
Because you want to make sure that squared is being applied to this only, not the whole thing.
I did this times that, and then I pressed enter, and then I divided it by this, and I used the parentheses. And then I multiplied by that. Is that right?
This I know is not right.
Yeah.
So
But I just need to
do this is my guess is that's where it got messed up. Oh, that shouldn't be that. That's 6.38 times 10 to the sixth.
No, that would be perfect.
I want everybody to try this. I want to make sure everybody knows how to use a calculator. So divide your answer by your mass, and you should see something you recognize.
The kilograms, right? The kilograms version?
Yep.
Yeah, I did that, and I didn't see it.
Now you gotta square the radius.
Huh?
Radius squared. The parentheses square. Okay. Good?
I don't know.
Yeah, you got it. Good. Good. Yeah. Nope. Nope. All right, where are we at here? Okay. This is not right.
This is what I got when I did it. Because I squared the 6 instead of squaring it.
It's not bad. This looks okay. This looks fine. I don't know what this is.
You don't know what this one is?
No, that's fine. The bottom here. I don't know where that is.
Well, what I did is I didn't put it in parentheses, I squared the 6, so this is a mess up.
Oh, okay. Do this in your calculator. Watch it.
Do I need to parentheses?
Yeah.
That's probably what it
I was trying to think so hard. I was like,
Oh, here we go. Here we go. Oh.
yeah, right.
You can't do the times 10?
No, that's fine. That's not. This is your calculator. It makes it so much easier. You see the E?
Yeah, do the second one.
Negative or not negative? 26
Yeah.
divided by. Nope. You just have to go straight up 13.
Oh, okay.
Okay. Now, no. Yeah.
Wait.
My pass is still
Yeah. And then you square that. No, you already squared it. Just kidding. And then now we're going to multiply that by G.
Oh, okay.
So 6.67 times 10 to the negative 11. Okay. How we doing? What number do we get? 9.8. Right after you divide it by your mass. Oh, you forgot to square your radius.
I did not get that yet.
Did you fix that? Oh yeah. Take that.
Divided by that?
Yeah.
I get 9.
0.8. Oh, 8.9. Yeah, some rounding. I don't know. Okay. All right. Here's the deal. This is true. Only true on or near surface of Earth. But this is true anywhere in the known universe. Okay, this is true anywhere in the known universe. Is on or near the surface of the Earth, somewhere in the known universe? Yeah, actually, the most known part for us, part of the universe. Okay, so this is a special case of this. Just like a square is a special case of a rectangle. So when we found this, that's the same thing as what we were doing first semester. So when you divided that by your mass, you should have found 9.8. Good with that? Okay. So what this enables us to do now is we can find the weight, how much we would weigh on any planet, on any moon, any star if you could stand on a star, based off of this equation. Okay. Now, one thing I want to do in this chapter, in this unit, is I'm going to give you a whole lot of facts and figures, and you're going to need to glean out which things you need and which things are not important. Because this is a really important skill in life. You've got a ton of information at your disposal through the internet. And you've got to be able to like weed out all the junk and like, here's what I need. Everything else, don't need it right now. Okay. So here's a bunch of stuff about Mars. How much would you weigh on Mars? What information is relevant to that question, which are not? Have we got an answer? Made your selections. Not a numeric answer, just okay. You need to divide this by 2 to find the radius, and you need this. You need your mass and nothing else. Good with that? Okay. We can also find the acceleration of gravity on any planet, on any moon, on any star. On Earth, we have that expression. So anywhere in the known universe, we have that expression. It's the gravitational force, attraction, is equal to mass times the acceleration of gravity on that planet. What mass do you think this is, though? Is this the mass of the planet, or is this the mass of the object that we're dropping? When you use this equation, was this the mass of the Earth, or was it the mass of like the apple or the ball or the skydiver? It's the mass of the object, the falling object, mass of the falling object. Good with that? Okay. Call that good for today. You got a worksheet, do, you know how to do a couple of those.